standard GMD4. This is one of the new standards in both courses of geometry. The standard is about visualizing relationships between two-dimensional and three-dimensional objects. Identify the shapes of two-dimensional cross-sections of three-dimensional objects and identify three-dimensional objects generated by rotations of two-dimensional objects. I see our calculus people going, yeah, I know this. Yay. This is a new standard on volume. There are two approaches to volume, really. We need to look at it from two different perspectives. Stacking principle and rotational principle, such as, how many of you have ever entered a building through a revolving door? Rotational volume is easily shown through the principle of revolving doors. Okay, that revolution, the rotation, fills in the shape, right? As a matter of fact, a rectangle will be rotating, revolving, and it will create the shape of a cylinder. Now, stacking principle. We can stack up any shapes like that. We can use coins. We can use this for demonstration today. This actually takes us to another standard that's also very important, GMD1 and even GMD2, Cavaliere's principle. In other words, look at this, compare the two stacks. Do you think they have the same or different volume?
Same.
How would you verify that?
Straighten up the.
We could straighten it up.
Or count the number of little squares.
We could also look at the slices, right? At the cross sections. If it's going to be parallel to the bases and it's going to be the same distance from the bases, and the slices or cross sections will be congruent. If they are congruent, then the shapes have the same volume. So a cross section is a very important part of volume. It's a very important concept. So we're moving on to our rotational volume activity. We're going to play with Play-Doh. We're going to make three-dimensional solids, cubes, pyramids, cones, spheres, cylinders. And we're going to use a ruler, or we have a dental floss to slice our figures and form cross sections. Let's get our hands dirty. Let's do this activity. You can even decide that one member of your group will be doing, let's say, cylinders, another will do prisms. It's up to you. See how many shapes you can make, and let's go for some very complicated ones.
Done this for, so.
Well, it's slanted, so it's going to be oval.
I think it's an ellipse or an oval.
So,
So, 1, 2, 3. So I still got 6.
what's really neat is Desmos, for example, where you can actually draw your three-dimensional figure, and then you can rotate it and see some of the cross sections. That's really cool
wonderful.
using technology.
Well, if you cut down
Straight
the middle,
down,
Right.
that's a rectangle.
That's
That's
a rectangle.
4. Wait a minute, hold on, that's not okay. It has
Think
to
about
be
the
2.
infinitely many sides that that thing has for the circle edge.
How did it end up being 4? That disproves us.
Let's find a good place to stop and talk about some of the things you have discovered.
We think that the maximum number of sides that the polygon cross-section can have would be the maximum number of faces that the three-dimensional shape has.
So you're looking at question number 2, right? Yes.
We were trying to answer number 1, and we at first didn't think, we thought everything was possible depending on what the shape was of your base for a pyramid. Because a lot of these you could make probably, depending on how you had a cross section. So, but we had a lot of discussion on whether or not you can make an equilateral triangle. or scalene or right
right
triangle.
triangle.
Those were the three things that we really got stuck on.
And so what was the benefit of this activity, in your opinion? The fact that you got stuck on those. What does it tell
Well,
you? I love that. I love that.
Well, we ended up going back and
Yes.
saying, recreate this and let's
Uh-huh.
try it a different way.
It just gave us
But-
an opportunity to do trial and error
Trial
and
and
to
error.
manipulate with what
And
we had
discuss.
and
Yes.
discuss about
It
it.
was a good opportunity to discuss different things.
We just discovered, we all kind of made our own shapes, like we divided up the shapes and played with the cross sections, and we recorded the different shapes of the different cross sections, and then we started focusing on the question about the maximum number of sides of a cross section. And we explored that concept, and I think we came up with the same conclusion that the maximum number of sides would be the number of faces of the three-dimensional figure.
With the exception of conics, we discovered as well that conics are, that doesn't work for conics. And what this activity did is cause us to ask again a lot of questions and get really, really engaged in the mathematics content. So it was really, really good activity.
Very powerful. And I also overheard your discussions about the vertical alignment of the standards. Let's start with the 7th grade.
In 7th grade, they actually do cross-sections of three-dimensional figures and rotations for volume of three-dimensional figures. And we used to do a whole set of stations where the students would use Play-Doh and do cross-sections with Play-Doh. They would use three-dimensional solids on an old-school overhead projector and look at the cross-sections that could be formed if you just lay it and see the vertical and horizontal cross-section. And then we did one that they would take like a two-dimensional shape on a pencil and then rotate the pencil. I can't really do it with this, but you rotate the pencil really quickly and you can visualize the three-dimensional figure that's created from that rotation.
Very interesting. And then we took it up
Right.
higher, right?
And then adding, and she referenced it earlier, but how in calculus, a lot of times students don't realize they've actually seen this prior. And if students were to explore cross sections, just the concept of cross sections of three-dimensional figures in this way, they can carry that into calculus where their cross sections may be different and they have to find the volume based on the surface of revolution. So definitely connections backwards and forwards.
One of the professors there created a model for us of a cube, and it had all of the cross-section pieces.
Just break it apart.
And it really brings it home to the kids because you can take it apart and they can hold all those in their hand. And because the Play-Doh is great, but it doesn't keep that shape that we want. The 3D printer it was amazing. And they could just take it apart.
Wow. Cool. That is a great idea. For those of us who don't have 3D printers, there is some technology that I would like to share. This right here is an interactive cross-section flyer, Applet. It's an interactive tool online. And what we can do is we can change the settings. You can choose a different, solid right here. You can change the number of lateral faces. And you can move slices. Let's take a look. See, it moves. Or you can just click animate, and it does it by itself. So that reminded me of that 3D printer you were saying, because you can actually see the slice so easily. That is cool, isn't it? You can then change animation right here. And you can even select to show identification of cross sections. This is, I feel like, was very helpful because you can see what shapes have been created.
Going, okay.
That might really be the next.
Yeah, I really like
closest.
that it has the coordinate plane there with it. You can see it better.
It's
that
kind of
way.
like seeing that slide, what you were saying. So this is a great web application. It's on shoulder.org. I think it's great to start with, playing with hands and exploring with Play-Doh. And then we can look at more precise and more exact, cross sections and things like that with the help of the 3D printer and this app online. So I highly recommend this. It's great. Just to close, what are your thoughts about this activity? Would you use it in a classroom? Would it be beneficial?
I think the kids would love it.
Yes.
Yes.
Uh-huh.
They love anything hands-on. And to give them something that they used or played with when they were a kid,
Uh-huh.
kind of brings the kid out in them,
Exactly.
and they love making the shapes.
Yeah,